In the world of probability, when events are dependent, we say that the likelihood of one event occurring is conditional upon the other event. And hence we establish this notion of a conditional probability. So one way we can think about this is, let's again kind of draw this pond and say in this pond we have green fish, and we'll just put two green fish in there and two pink fish. I hope you like the fish that I'm drawing. So there we go. And let's go ahead and add one more. There we go. All right, so now we want to figure out what the probability is that we draw a pink fish and a green fish. And we're going to say that these are going to happen in this particular order. So pink fish first, and then green fish second. Okay, now these are actually sets. The probability of selecting a pink fish is actually the set of all pink fish, and the probability that we select a green fish is the probability of this event occurring, that we draw a green fish. Now, we would want to write this as the probability that we draw a pink fish, and I'm going to assume that this is the first fish we draw, that we want this particular sequence, multiplied by the probability of a green fish. Now I'm going to leave this open-ended for a second because we're going to add something in here. Now, the reason we're going to do that is because if I say, what's the probability of drawing a pink fish, one might say that it's 4/6. If I tell you nothing else, and I just say, what's the probability of drawing a green fish, you might say that this is 2/6. But if I tell you that these are not being replaced once we draw them, in other words, we say that this is a situation where we have no replacement, then your assessment of that probability is going to change. In other words, if I don't throw that pink fish back in, that reduces the size of my pool. But when we write the probability of a green fish without specifying any other condition, that probability is 2/6. Now you might say, but that's crazy because you just told me you drew a pink fish. However, this probability statement does not have that condition built into it. So what I will do is I will put this vertical line down here, and this vertical line is read as given, or given that. And what that means is that I want to know the probability of a green fish being drawn, but I'm going to give you a condition. And the condition is that a pink fish has already been drawn from the pond. So now that probability is conditional, and this is a conditional probability statement right here. So this is what we call a conditional probability. And the condition is what we list to the right of that vertical bar, which stands for given that. So I'm being a little bit sloppy here in this notation, but I'm emphasizing that the probability of selecting a green fish, that's what the event is that is up for grabs. But I'm telling you that a pink fish has already been drawn. So as you look at this, you might say, well, okay, suppose it's that pink fish right there. And therefore, the probability of drawing a green fish, given that a pink fish has already been removed from that pool, is no longer 2/5. It is now it's not no longer 2/6, it's 2/5, because I've given you the condition that one fish has been removed from that pond. And so, of course, that gives me 8/30, which is 4/15. So we'll just leave that probability statement in that sense. So a conditional probability is often written like this. It's probability of the event that you want to happen, and then this vertical bar, which stands for given that, and then some condition right over here. And one other way that we could think about this 4/6 times 2/5 is the numerator expresses the number of ways that we could draw a pink fish and then a green fish. So 4 times 2 is really saying each of these 4 pink fish could be paired with one of 2 possible green fish. So really there are 8 ways in which this could happen. Similarly, the number of ways the sample space can happen is, well, in the first slot, we could draw one of 6 different fish. It could be any of the 6 fish. And then for the second fish that's drawn, we only have 5 possible options from which to draw. So really there are 30 different combinations, or maybe I shouldn't use the word combinations, but 30 different ways we could select 2 fish from this pool. And when we divide those, we're merely saying, well, we counted all the number of ways we could get a pink fish and then a green fish, and in the denominator we counted the total number of things that could occur when we draw at random 2 fish from that pond. Now, back to this, the probability of an event wanted given some condition. So to give an example of a situation where this might change in the real world, let's say that the probability of a car accident on any given day is in a particular city is going to be 2% or 0.02. Now, if I write the probability of a car accident, given that there's rain, what do we suppose is going to happen to that probability? It was 2%, just in general. If we counted all the days that people were out over a certain period of time, and we noticed that 2% of those days there was a car accident observed, what about the days on which it rained? So my condition here, my sum condition, is that there's rain. And I'm going to anticipate that this probably goes up. Maybe not a whole lot, maybe it goes up to 0.035, where there's a 3.5% chance that there's a car accident if there's rain. And then similarly, I could say, well, what about not on any given day, but on only those days where there's no rain? What percentage of the time was there a car accident? I might find that this is actually a little bit lower. Maybe this is 1%. Now this 2% here just takes all the days. This is across all days. While these two different conditional probabilities tell me the percentage of time that there's a car accident on days with certain conditions. Now, I don't know that these numbers are accurate, but they at least illustrate the fact that the likelihood of a car accident, if you could tell me whether it's raining or not, I could assess, do I need to be more cautious? Is it more likely that I'm going to get in a car accident if I am out there when it's raining versus when it's not raining? We could also look at the conditional probability in terms of a contingency table. So let's just say hypothetically here that I take a survey, and down here I'll put 1.00 to indicate that this box represents 100% of the people I've surveyed. And D will stand for the set of all people who have a dog. And I'll say that C is the set of all people who have a cat. And from this table, we can see that in this box right here, if we imagine this to be 100 people, then 35 of those 100 people surveyed responded that they have both a cat and a dog. In this cell of the box, we could see that 40% of people have a dog and they do not have a cat. Here I can see that these 15% of people have a cat and no dog, and then 10% have neither. If I wanted to know all the people who have a cat in the 100%, then I can take the sum of these two and see that this is going to be 75% of the people I've surveyed have a dog. Some of them also have a cat, some of them don't, but 75% of people interviewed have a dog. Now, that means only 25%, that's 0.15 plus 0.1, 25% of people do not have a dog. And similarly, 50% of people have a cat, 50% of people do not have a cat. So if I wanted to know, for example, what's the probability of somebody having a dog and a cat, well, I could grab that from the table here, which is 0.35. Now, the way I would normally calculate that is I would say, okay, if I assume independence, if independent, then I should be able to take the probability of the percentage of people who have a dog and multiply that by the percentage of people who have a cat, which would be 0.75 times 0.5. Well, that gives me 0.375, and we see a problem. Namely, the problem is that these don't match up. So what does that allow me to conclude? Well, that pretty much tells me that this 35% I know is right. I mean, that was the data that I collected. 35% of people responded that they had both a dog and a cat. But when I use the probability of a dog multiplied by the probability of a cat, I don't get that same answer. And that's going to tell me that these events are not independent. So since the probability of a dog times the probability of a cat is not equal to what I know to be true, these events are not independent. So if the product of the two probabilities does not yield what I know to be true, then these events can't be independent. Well, how would I calculate this then? Well, what I really should do when I'm calculating probabilities is to assume that they are not independent unless I'm told otherwise. So under dependence, the way I would calculate that probability is to say that's the probability or the percentage of people who have a dog multiplied by the percentage of people who have a cat, given that I know they have a dog. Because the people who I'm studying here, I know they have a dog, and now I want to calculate the probability of having both a cat and a dog. So it seems that from this calculation over here, that the two events are not independent. In other words, maybe people who have a dog are more likely to have a cat, or who have a cat are more likely to not have a dog. Well, I can figure out what these probabilities are. I know that the probability or the percentage of people who have a dog is 0.75. But how do I update this probability here? Well, out of the people who have a dog, which is this 0.75, out of the people who have a dog, 0.35 of them have a cat. Now, if you notice what happens here, knowing that we're only looking at people who we already know have dogs, that's the 75 of the 100 people, if you will. 35 out of 75 people are actually dog owners who also have a cat. And we can see that these two probabilities here cancel, and we're left with 0.35. We could also calculate the probability of having a dog and not having a cat. So that's the percentage of all people who have a dog. And now that we know better, we should say, okay, now we need to know of the people who have a dog, what percentage do not have a cat? This is going to be 0.75 for the probability of having a dog, independent of any condition, multiplied by the percentage of people who do not have a cat out of the people who have dogs. Okay, well, that's going to be 40 people out of the 75 who have dogs, 40 people of them do not have a cat. So if I take 0.4 out of the 0.75, then once again, what we notice is this comes out to 40%, which matches what we know to be true. Once again, if I took 0.75 times 0.5, I would get 0.375, and that doesn't quite match what we have here. So it really suffices to show that you do not get any one of, pick any one of these cells, and by multiplying the two probabilities together, namely 0.5 and 0.75, if you do not obtain the value that's in the table, that's one way to know that the events are dependent. So we'll go ahead and leave it with this one final remark. We'll say that in general, the probability of two events jointly happening, we'll call them A and B, is the probability of one of the events happening multiplied by the probability of the other happening, given that we know the first has happened. Now, if the probability of B, given that A happened, in other words, the likelihood of this event B happening, if we know that event A is true, if that equals just the probability of B, meaning that the effect of A is negligible, it did not affect the likelihood of that outcome occurring, well, then that means if these two things are equal, that means up here I could replace this probability with just the probability of B, and if the likelihood of event B happening given A is independent of A, then that means that A and B are independent.